So thank you all for being here with me late on a Sunday afternoon. I appreciate it. I know this is the last talk of the day, and people are going to be filtering out and going home soon. So I'm going to be talking about the past, present, and future of automated remediation. My name is Dan DeVella. I work for a small startup called Pixie. We're largely based in the Baltimore area. One of our founders is in this area. My role there is as the lead engineer on our automatic vulnerability remediation service. And so we are focused on application security fixes. But this talk is going to, cover a sort of broader view of the world and talk about remediation in general. So if we're doing past, present, and future, we're going to start with the past. But I want to say, I think that to this crowd, to a security-oriented conference, remediation has a specific meaning, or potentially many specific meanings, and it's very much focused on fixing security problems, making them go away. And there's a bunch of different security domains where we care about fixes. There's application security, obviously. There's you're going to fix your own code. You want to fix third-party dependencies that have problems. There's container security. There's all kinds of ways and things that we want to fix. But I think what is common to all of these kinds of things, and when you take a broader view, when we talk about automated remediation, is we're really talking about code that is able to make changes to other code. And when you look at it that way, it's something that's not really a new concept. And in fact, it's kind of surprising how far this concept has gone back into the past. So, again, looking at it broadly, in the 1950s, Fortran was introducing what we would call compiler optimizations. And this really is code that changes other code. The focus at that time wasn't security, it was optimization and making sure that your code ran as efficiently as possible on the hardware that you had. What's really impressive about this to me as an engineer is when you look at the amount of computing power that they had and they were able to do these kinds of things, it's just really incredible engineering, and it really puts me in awe and makes me a little ashamed of my own capabilities, but it's cool stuff. When you look ahead a little further and looking into the 1990s, we see that Smalltalk introduced an IDE which was able to deliver highly directed but automated refactoring. And I think this is the kind of refactoring that all of us would expect from our modern IDEs, the kind of thing where you have a method name that you want to change, you want that change to take effect automatically across your entire code base. It's something that can be done automatically, but it's fairly tightly scoped, and again, not necessarily security focused. Although you may be using that to fix a bug or a vulnerability. It's really only indirectly security focused. Where things start to get a little more interesting is more recently in the 2010s, we have tools that developers are using for linting and code quality that start doing more than just reporting the problems that they're finding. They actually are proactively fixing those problems. And these tools are capable of identifying security problems. Some of them might start fixing some small, very tightly scoped security issues in some very limited cases. But this is very useful to developers, and it's something that is probably familiar to most of us today. We also see around this time the introduction of open source, quote-unquote, code mod libraries. Code mod is a pretty common term now. But we see these first generation libraries like JS CodeShift, CodeMod for Python, and Spoon. And these have a little bit of a different emphasis than the linters and other code rewriters. They're intended as frameworks that enable developers to write custom code changes. So you can write, if you have a particular rule or code quality thing that you want to enforce, and you want that change to be made automatically, you can write a plugin using these frameworks. And they also tended to have very large open source libraries where people could contribute and share different things that were useful to them. So this is where things start to get interesting, because you can imagine people starting to think in terms of a security focus. How could I write a code mod that might fix a common insecure pattern that I encounter in my code? And then when we look at 2020, there's this project called C3PR, which I wish I had come up with that name for that project. But the idea is that it's going to send pull requests that fix sonar issues. So this was an academic team. It's a GitHub bot that they built, but I assume many of you are familiar with sonar as a code scanning tool. It finds code quality issues. It also finds security issues. And their goal was to automate the remediation of those issues. So taking the output of sonar and creating pull requests that developers can merge. It's worth noting that this actually was done, very shortly before the age of the explosion of generative AI, and so they were doing this in terms of deterministic code transformation, syntax tree transformation, which is really cool and very impressive. And then even more recently, we see what we're calling second generation code mod libraries. So this would be frameworks like Open Rewrite. There's libcst from Meta, and CodeModder, which was actually developed by Pixie. So this expands the capability of automated code changes, automated remediation. We're going to talk about each of these things in a little bit more detail. But the takeaway here is that these are very expressive code changing frameworks capable of fairly sophisticated transformation. And again, they're pluggable. Developers can write their own transformations and do things that are useful and interesting to them. So one of the big takeaways for all of these kinds of changes is that, for lack of a better word, they're relatively simple or they're relatively easy to describe. And what we mean is that they had very low contextual requirements. A lot of these changes are what you might think of like as, like a peephole optimization in a compiler. It's just really looking at a single line of code, or maybe optimistically, it's looking at a function body or a method body. But it really doesn't need to see the entire code base. It can operate on very limited information, and it can create a very reliable change. It's a change that in almost no circumstances are you going to look at that and think, wow, I don't know what it was doing. I wish it hadn't done that to my code. And the trade-offs here are that it's highly reliable and highly predictable, but very low flexibility. So what we mean is that it's only capable of identifying certain shapes of code, certain very specific syntactic elements, and applying itself to those. And that means that I think as security practitioners, when we look at the kinds of changes these things tend to make, it's just not that interesting. It can't solve the kinds of problems that we feel like we need to be automatically remediating in order to make our code safer and our application safer. So that brings us to the present. And I'm going to show this diagram. I think that this is a diagram that a lot of us have in our heads about what self-healing software or truly automated vulnerability remediation should look like. So depending on your security domain, you're probably using SAST or DAST or other kinds of defect detection tools. There's also, lots of other inputs you can imagine here. There's bug bounties, people identifying bugs that way, pen tests. There's lots of ways that we can identify problems with code. And in order to have a fully automated solution here, we need to take the output of those processes, whether they're automated code scans or human-driven processes. We need to identify the asset that those problems apply to. So we really mean, like a particular application or maybe a particular container or a particular cloud environment. And we want to go fix that problem, and for the purposes of this talk, that's going to mean changing code. We want to change the code. And then we want that change to be automatically, reflected in our production environment once it's merged and ready to go. And ideally in this automated process, at the end of the day, once you deploy that fix that's been generated, the next time your scanner tool runs or the next time somebody does a pen test, they're not going to find that problem because it's automatically been remediated. So I think this is the mental model that a lot of people have and aspire to when we think about self-healing software and automatic vulnerability remediation. But there's a couple problems with this picture that I'm going to point out. One is that if you fix things that weren't actually bugs, you're going to cause even more problems for yourself potentially, or at the very least, you're going to cause somebody a big headache. So the example I'm going to show here is when you have a tool that has overzealously identified a reflected XSS vulnerability in your web form or your in your web page, and you see something like this. And this actually happens to me all the time because I have an apostrophe in my name, and I'm not going to name names, but a very large online web store sends me emails that look like this all the time because they've overzealously sanitized. So at worst, it's annoying for users. It's wrong. At worst, you're annoying your developers because they're making changes that shouldn't really need to be done. But actually, I should say even at more worst, you've created a bigger problem potentially. There's some cases where this may actually introduce a security vulnerability where there was none before. So again, fixing things that aren't actually problems is a problem. So that's kind of something we need to be aware of as we automate these processes. So I'm going to propose a different picture here, which is a funnel rather than a loop. So one of the first things that we need to ask ourselves before automatically fixing something, or this automated system needs to ask itself, is this actually a bug? So we found in our own studies and our own experience that the common static analysis tools that are being used in application security they report 50 to 80% false positives depending on the application they're looking at. And I think if there's anybody in the audience who is using these tools, who's an application security practitioner, I would expect that resonates very much with your lived experience. The other thing that we need to be asking as part of this process is, what is the real severity of the finding that has been identified? So, a tool might see a particular code pattern, it might see something that looks like a problem, but if it doesn't have the full context and the full, business case and where this fits into your architecture, it can't really tell how big of a problem this actually is. Like maybe you've identified a problem in a web form or something, but it's a purely internal tool that is not expected to be exposed to an external network. That's important information that we need in order to determine how badly this thing needs to be fixed. So then we also need to determine what is the safe and effective fix. So for the things that are real problems, what does the solution look like? We feel that we're pretty good at this. Coverage is not 100%, but there's a lot of vulnerability classes that are remediable, and that you can propose an actual fix and do it automatically, and that will be acceptable to a developer. So we're funneling down into actually doing fixes now. And then we need that fix to be automatically deployed. So I think a lot of developers would agree the right way to do this is as part of CI/CD processes, but there's a lot of tools, or I should say a lot of teams out there that may not have quite the maturity that's needed to completely automate the process of a change being merged to that being automatically deployed, and then that problem no longer being in production. And then there's some compliance requirements where there may be reasons that there needs to be a human in the loop to automatically, or to not automatically deploy something, and it needs to be approved. The person who made the change needs to be different from the person approving the change. So that's another part of this process to be aware of. And then, of course, we need to confirm that the problem is gone. In some cases, this might rely on your CI/CD processes. If you are automatically rescanning after deploying, then you would expect a bug, or you would expect the finding to go away once the fix is merged. But again, we pointed out some of these processes that are very manual. If it's a pen test, or if you've relied on bug bounty, then there's got to be a human who comes back and confirms whether that bug is gone or not. So these are all things that need to be part of our picture as we come up with as we move towards our goal of true automated remediation, and which parts of these can we automate, and how can we make things better. So looking at the top of the funnel for accuracy and severity, I'm going to take a moment to talk about AI-based triage. So again, remember, we're seeing that these scanner tools are identifying a huge volume of false positives. There's a lot of reasons for that. There's some incentives for the tool developers to have that kind of behavior, and I'm not here to judge that because I've worked as a tool developer myself. Part of the problem is that when you are evaluating a security tool, you probably have some known test set that you're running against. It probably has some known problems in it. And if that tool does not find the problems that you know about, you're not going to think very highly of that tool. So the bias is towards detecting true positives, but the effect is that the tool is going to detect many false positives. I think there's also a sort of a bigger incentive there, or a different incentive, which is that the tool vendor has this is this thing on problem. Like when you scan something for the first time and you're evaluating a tool, if it doesn't report anything at all, then again, you're not going to think very highly of that tool, even if there really is not very many true problems to identify. What I'm really trying to say is I think the tool vendors do not have such a big incentive to solve this problem themselves. But there's also technical issues, which is static analysis tool is looking at source code. It doesn't have access to like your business context or the technical context. It doesn't know that this is like a microservice that's talking to 5 other microservices. It just doesn't know any of that. It can only see the source code, and so its view of the world is limited, and that limits what it's able to tell us. So what we found is that we can leverage generative AI to very effectively triage tool findings. This is an example of a insecure randomness finding in Apache Roller, which is an open source Java application. And I think if a human is looking at this code, you're going to see, okay, the tool is telling me there's insecure random. I can see that there's credentials involved in this somehow. So this is probably something that I want to pay attention to, and potentially something that I'm going to want to remediate. But what's really cool is in this particular example, our tool was able to use broader context by looking at the actual dependencies being used by this application, and determined that even though the code itself is not using secure random explicitly, the dependencies are set up such that a true cryptographic random is guaranteed. And so our tool has determined that this is a false positive. And that's a very powerful thing because, first of all, it means that you don't need to distract a developer with trying to fix this. If you're using an automated remediation solution, you won't get a spurious fix from that, where a developer now has to review code that really isn't meaningful or useful. That change is irrelevant. So this solves a big part of the problem, we think, in terms of filtering for true positives versus false positives. But this triage process also applies to severity. So it allows, we can take a look at a tool finding that may be listed as high severity, and we can determine based on context that it's actually in fact low severity, and that's going to impact your prioritization of this issue and how you treat it. So that solves the top of the funnel, we think, by limiting the number of fixes that actually truly are problems and need to be fixed. So in terms of current practice, I'm going to shift gears a little bit and show what some of the state-of-the-art is in terms of automatic code fixes and automatic remediation. So a big part of the picture is modernization. Which means, and this has huge security implications, you want to make sure that you're using the latest frameworks that are still supported, have security support, and are being regularly fixed and improved. And in a lot of cases, migrating from one version of a framework to another is not as simple as bumping a version. There's very large API changes that can have huge impacts across your application. And so there's this open source project called Open Rewrite, which is developed by a company called Modern. And they have spent a lot of time and very impressive engineering effort in building tools that are capable of these very large-scale refactorings and migrations. And so they are doing this mostly, at least when they started, it was almost entirely deterministic syntax tree transformation. I believe that they have recently been starting to use generative AI. I'm not sure exactly in what capacity, but again, this solves the problem of like making large sweeping changes to a code base and doing it safely and effectively in order to modernize the framework, the frameworks being used. In the more explicitly security domain, there's a framework called CodeModder, which again is developed by Pixie. And the original intent of CodeModder was to be both a detection and fixing framework. So the tool used an open source rules engine to identify potential security problems in the code, and then fed that into language-specific syntax transformation libraries. So for Java, it's Java parser. For Python, it was libcst. And this was intended to proactively make fixes to code bases to harden against common security vulnerabilities. So you're seeing an example here of a SQL injection vulnerability being remediated. This change that you're seeing is it's entirely deterministic using code transformation. There's no generative AI involved in this at all. So you can imagine there's a lot of engineering effort that goes into making a fairly sophisticated and safe change like this. But it's really cool to be able to harden and secure against these common security problems. And then in a completely different vein, I think it's 2025, and we're seeing the proliferation of AI-driven, generative AI-driven software engineers and co-pilots and pair programming tools. So this is one particular example of this called Aider, which is open source. And so the idea is that Aider is a AI pair programmer. You're going to give it instructions in the form of really natural language, like you might tell another engineer, and it's going to go and make changes for you. Actually, if I could just get a show of hands, I'm not sure how many developers there are in the audience, but how many of you out there have experimented with any tools like this? There's, GitHub Copilot, Cursor, there's Claude Code. Okay, so like these things are really starting to take off, and the purpose of this talk is not really to argue about how effective or how secure, whether we're all going to be replaced by AI agents next year or something. But it's really changed the game in a way to see what these tools are capable of, and to be able to make the kinds of changes that they can. One of the interesting observations I would like to point out about these pair programming tools is, at least in my experience, I think a lot of the community seems to be agreeing on this, they're really pretty effective at greenfield development. Like if you just have an idea and you want to create something new and you can describe it pretty well and maybe the terms that a product manager would describe it, it's going to do a really pretty good and almost scarily impressive job of writing an app for you that actually kind of works. And I think it's amazing how quickly we've lost sight of like how incredible that is. Like imagine saying that to yourself like 5 years ago, that there's like a computer program that you can run on your laptop that can just write like a fully fledged web application and get it up and running. Like that's very impressive. But however, I do think that these tools struggle a bit in environments with existing code. They struggle with high context kind of changes where it needs a lot of understanding of what the code does and how it fits together with other components. It may not be able to fix bugs unless you already kind of know where the bug is and where it should look. So these things are, they're very impressive, but not necessarily capable of just making very sophisticated, very high context changes quite yet. That does raise the question, however, as we're looking at automatic vulnerability remediation and we want to be able to make changes to code. How are we going to decide whether that solution should involve determinism, meaning traditional code transformation libraries and frameworks, versus using generative AI? And so I just want to point out a few comparisons here. So for code transformation, again, think JS CodeShift or libcst or these other AST and CST transformation libraries. The changes are, in general, highly predictable, highly reliable. So if you run it 100 times on the same code, it's always going to do the same thing, and you should be able to know exactly what it's going to do. The downside of that, though, is it's highly inflexible. So if somebody has not explicitly programmed your transformation for the code shape that it's about to encounter, it may not do anything to it at all. Or even worse, it may do the wrong thing to it. So it requires engineering to build the right solution, and it especially becomes difficult to support very broad use cases. And the effect of that is that it has high marginal development costs. So if I'm working in Python and I want to remediate SQL injection automatically, I have to support all the different ORMs that I know about. I have to support all the different ways of building queries and using APIs. And again, that's just for one language, for many frameworks. If I want to build a new rule that remediates reflected XSS or something else, that requires like a whole new engineering effort to get that up and running. On the other hand, we have generative AI, which I think we would all agree is fairly unpredictable in its output, also fairly unreliable, at least with naive approaches. But the flip side of that is it's highly adaptable. I don't need to write 5 or 10 different rules in order to tell it to remediate SQL injection in Python. The model itself likely has enough context to be able to take whatever it's looking at and extrapolate and determine what framework it is and come up with a passable change. And so the effect of that is that there's relatively low marginal development costs because I can build something that's very adaptable and going to handle a large number of edge cases with a lot less effort than I would need for the traditional code transformation. And kind of in both columns is like, sometimes it's wrong. Both of them are going to be wrong in certain cases. The code transformation is going to miss edge cases that I haven't accounted for, and it's going to make some wrong transformations if I haven't fully accounted for different code shapes. But generative AI is going to give garbage, sometimes like complete garbage, or sometimes just bad fixes, or it's going to add a bunch of stuff that I don't want to my change. So to enumerate that a bit further, there's a whole lot of failure states that we need to account for if we are going to build automated remediation solutions using large language models. And we've listed a couple of them here, but it's all the way from the layer of like, oh, I just couldn't make this network connection right now, or I timed out, or I used too many tokens, or something like that. If we're building software using generative AI as a component, we really need structured data, and there's often times where the models struggle to give us the structure that we expect. One of the approaches that has been explored a lot in open source and also with ourselves is asking the models to generate diffs for fixes, because if you can tell it to structure its changes in a particular way and you can get a diff, then that's very easy to take and apply to a code base. But that's a fairly complicated task for a large language model. It's going to do things like give you a diff that is not a valid diff, or it's going to give you a diff that has invalid code or changes that you don't want. There's this term hallucinations, where it's just going to make stuff up and you don't know what that's going to be. And then specifically for code changes, we see a lot of things where, it's trying to be very helpful in a lot of cases, but it'll put placeholder code where a developer needs to come in. It thinks that a developer needs to come in and finish the job, or it's going to add to-dos for you, or it's going to remove your comments that you don't want it to remove. It can break APIs. It can do all kinds of things. And so for the failure states that are enumerated just here, and this isn't exhaustive, if you assume a reasonably good success rate of 90% for each of these things, if you are doing just like a single shot request to make a fix, when you account for all of those things, the probability of that fix being correct is really pretty low. It's 34%. And I can speak to this from personal experience. When you try to apply fixes across large code bases or large numbers of findings, you're going to see that it just doesn't do that well. However, there's a lot of opportunities to use really clever software engineering to improve those results. So I think I'm just going to pause for a quick aside here, but it feels like, especially when we talk to security practitioners, there's a pretty large amount of skepticism about generative AI, and I think there's good reasons for that. I'm not going to ask the audience to raise your hands and say if you agree or not. But I also think that there's this image of just somebody's going to take this and just paste it into ChatGPT and say, hey, give me a fix, and I'm going to throw that into my editor and create a pull request, and that's going into production. And it turns out that I'm not saying people don't do that. I'm sure people are doing that. But when you're building a product or when you're building software that is using generative AI as a tool, it actually requires a lot of engineering, and it's not doing things that are quite as naive as saying here's the vulnerability, just give me some output and I'm going to throw that into code. There's a lot of systems and a lot of feedback loops and a lot of things that we've built to try to constrain the output and to try to direct it towards correct fixes, and then to validate that those fixes are actually good and correct and safe and effective. And before any of that ever, again, in an automated process, before any of that is ever presented to an end user. So there are very much, I think, good engineering practices and clever things that we can do to dramatically improve this rate of success. And some of our own benchmarks internally, for example, I've got a benchmark that has a large number of SQL injection vulnerabilities across a lot of different languages. I see a 95% success rate based on our own metrics. So that's all engineering that we're applying and using these models as a component, but building a lot of software around it to constrain the solution. So another approach that we've explored is using hybrid approaches to code changes where it's not solely generative AI making the change. So the sort of naive approach that maybe we've tried in the past is saying, I want the LLM to give me a diff. I'm going to tell it what the problem is. I'm going to tell it where the problem is. I'm going to give it some good context and tell it how I think I want it to remediate it. And just give me a diff. And what happens is the LLM will give you a diff, and it's wrapped in JSON because you need structured output to be able to work with it. And that problem is really pretty difficult for an LLM to solve reliably because you're asking it to generate JSON, you're asking it to generate a diff correctly, you're asking it to get the fix right. There's a lot of moving parts and a lot of tasks, and doing that as sort of a single shot prompt is not necessarily going to be really effective. Something that we found to be somewhat more effective and opens up a lot of possibilities is instead of asking for the code or instead of asking for a diff, we ask it to generate instructions that a human would use to remediate this vulnerability. And we can not only do it in a human readable way, but we can ask it to also generate machine readable instructions. And so this might look like something like, remove statement on line 39, in this example, add string parameter foo to line 40. And what we can do you can do a variety of different things with this output. One of the things that it turns out to be pretty effective is feed it back into another model or another prompt and use that as the input for the change rather than having one giant task that it has to do. But another thing that we've actually done with this is when it's in a machine readable format, we can actually feed that to one of the transformer libraries that we've talked about before. like JS CodeShift or libcst or Java parser, and use this context to direct a change that would have been difficult to do otherwise. So in these cases, we're really asking the LLM, we're relying on the LLM for its problem-solving ability and its context-gathering ability, but not necessarily for its code generation ability. So I think that this is really pretty cool, and it's a very effective way to make changes that are very reliable and, if not quite deterministic, they're highly predictable. Just to shift gears to something else we need to consider when doing automatic vulnerability remediation. There are different kinds of security fixes have different what we refer to as blast radius. So there are changes that may be very simple to describe, and that change may have an impact that is limited just to the code that you're changing right there, or it may break your entire application. And so for one example of the former, if you disable external entities to prevent what would this be, XXE or another XML-based vulnerability. I mean, there's probably almost no code out there that is relying on external entity expansion or resolution. And so this isn't a real wager, but this is a change that can be made very safely, very reliably, even if in theory it could break somebody's code somewhere out there in the world. It is highly unlikely to do so for most code bases. However, for a different example, if I take some random line of code and see that it's using MD5 for password generation, and I decide, oh, I know what I'm going to do. I'm going to change that to use bcrypt because bcrypt is really secure. Your app is just never going to work again, right? Like you're going to have to do a database migration in order to make this work, and all of your current users are going to be affected until you make that change. So even though both of these changes in and of themselves are really simple to describe, and really both of them can be done with very simple deterministic transformation, they have very different blast radius, and we need to be able to discern that when we make the when we do automated remediation. I think that the second change is something that we aspire to do correctly, and I think it will be within reach for us sometime soon, but it's not something that we are capable of doing today. It raises the question, though, of what percentage of the problem can we address today? And so in our own studies, in our own case studies, and looking at customer and open source data, we have found that about 50% of findings can be triaged to a false positive or a low severity, something that a developer or a security engineer doesn't really care about. It doesn't matter very much whether it gets resolved or not. And then we found that 38% of things from the average SAST scan is something that we can remediate automatically. And that could be using deterministic processes, or that could be using generative AI processing. If you expand beyond just the security domain and look at linter type findings, code quality type findings, then we can do even better than that. Okay, so that brings us to the future. This is where we get to make some educated guesses about what's going to happen next and what we'll be capable of doing next. So the first prediction I'm going to make is that generative AI is going to continue to be very important for automated vulnerability remediation. I think we're very near the point where generative AI-based code changes is going to be almost completely commoditized. There's going to be all kinds of tools that are capable of making code changes based on reasonably descriptive prompts. And so that, out in the community, you'll see a lot of discussion about, AI scaling walls, like how much better can these models really get, or have we kind of tapped out everything that LLMs can do? Do they, just not have any more data out there to make them improve? And I think that there's some good arguments there, and I'm not going to weigh in on that because I am not an AI expert. However, the one prediction I would make is that I think that these models are going to get cheaper and cheaper and cheaper and faster to run, and that the cost of prompts and the cost of tokens, and both in terms of money and time, is just going to continue to go down. And so when you look at it that way, I think what we're going to be able to do is make very small, very targeted software components that are using generative AI under the hood, and we're going to be able to piece a whole lot of those things together to build more and more powerful and more context-driven fixes, and all kinds of things. But specifically in the remediation domain, it's going to become more and more powerful. Our CTO and co-founder, who has given this talk in a variety of different settings, has compared this to, it's just kind of a stretch goal, but what if you imagined a model scaled down to the size of a transistor, and you have the power of combining these things in very complex and interesting ways. So I do think that using generative AI as a component of software is going to be more and more of a thing going forward, and that's going to enable more and more interesting things. However, I think that what's really going to make automated remediation more and more effective is adding more context to the kinds of changes we make, and using more and more outside sources of data to inform the kinds of changes we make and how we make those changes. So you can imagine, looking forward a little bit, that a very intelligent system would be capable of integrating context from a whole bunch of other systems. So, maybe it wants to read Slack messages that have discussions of a particular feature. You have Jira tickets that describe how something was designed or how something should be fixed. We can have other knowledge stores that it's looking at that might have coding standards or security policies. And then we anticipate getting feedback from the SCMs themselves, like GitHub or Bitbucket, like, did this build pass? What was the failure if it didn't? And then also having tighter and tighter integrations with the SaaS themselves. So getting more and more context and bringing all of that to bear on this problem is going to help us generate more effective fixes. And then there's also, in the generative AI and LLM development world, this concept of agent tools, which is giving the models abilities to choose what kind of information and where it wants to look for information. So it may choose to look for context in different places, or go out to the internet, or maybe it wants to generate some code that it can run itself and test it out. And then we also anticipate interaction, where maybe a developer leaves a PR comment that says, hey, this fix looks pretty good, but I need you to change this little thing, and that's automatically going to be taken into effect by the system. So we think that where we're going is something we're calling the magical fix cognition stack, where we have all kinds of sources of data, and where the really interesting problems is going to be for us is integrating all of those sources of data. And there's going to be a huge amount of competition in this area. So who can gather the most context from your organization, from your tools, and from all these other sources to generate the most effective fixes that we can. And the more information that we have, the more context that we can use with remediation. So there's like business cases, or what is the role of the business component that needs this fix to be made. I think there's going to be all kinds of information that becomes available and that we feed into these processes. And then, at the end will be whatever the model wants to do with that, which in a lot of cases we hope is fixing a security problem. So for very high-level predictions, what do we expect to see? So in application security, we expect to see a shift towards using intelligence to drive remediation-centered solutions rather than just detection. So we are already seeing that. Remediation is very important. It's not enough to just find problems. We need to fix problems as well. We're also going to see a move away from, when using generative AI, We're not going to use fine-tuned models. We feel like there's a lot more to be gained from using reasoning models and relying on the context and knowledge that already resides in those models rather than fine-tuning it ourselves. And we expect to see a dramatic rise in the percentage of vulnerability classes that we can fix. Again, with fixes that we'd consider magic today, becoming commonplace in the very near future. So for that, I would refer back to the example of changing the algorithm used for hashing passwords, and with that becoming something that maybe we can't do it today, but maybe next year that's going to be a very effective and reliable change that we can make. So that's my talk. I think my timer says I've only been going for 25 minutes, but it's 3:45, so I'm not sure how to square that circle. But I'm happy to take time for questions. I know there's another wrap-up session in just a few minutes here. But thank you again for being here today. This question?
How soon do you think it is that it becomes a requirement that you know how to use it?
So are you asking like that it's like a compliance requirement that you're required to use automated remediation?
Like a skill in a job description section for you to apply for a job.
That's a good question. I'm not too sure about that. I think the expectation is that as a security practitioner, you need some way to remediate these things, and whether that's being done manually or by another tool. Right now, I don't know that anybody is dictating that, but yeah, good question. Question there.
Not to deter away from maybe what Pixie does at all, but I think that you mentioned sonar, do a lot of scanning with sonar. I don't necessarily recall what the latest is for sonar, but if they were to integrate Gen AI and maybe that hybrid approach you described, you think that would be a big step forward in this space for all the existing sonar users?
So you're asking if Sonar itself provides its own remediation solution?
Yeah, I mean by integrating Gen AI in a hybrid manner that you described.
Oh, I see. For the actual detection part of it? Yeah, I do think that security vendors and SaaS tool builders are going to start using generative AI in combination with their traditional static analysis processes. I think that they will use it to fill in places where not enough context is available to a traditional static analysis tool, and that should lead to better and more accurate results. I'm not sure how many are looking into that right now, and I'm not sure if it's going to be the existing vendors that do that or whether it's going to be some new players that come along and build new things that they can sell as being more accurate and more reliable. But yeah, that's a good question. Sorry, I saw that one back and back first.
You mentioned like improved performance when you use multi-model architecture type of thing. Other than improved performance, was it more costly to also use multi-models or any other observations?
Yeah, and let me clarify because I think I may have misspoke. It's in general we use we do use multiple models from multiple model providers. But what I really mean is like having multi-step prompts where it's not just like one giant prompt that is fed to the model and then you expect for like a nice packaged up answer at the end. We need to break that down into different problems. So you ask a question here, and then depending on the answer to that question, there's going to be a decision tree, and you do something different here, do something different here. But yes, to answer your question directly, yes, that increases the cost. Yes, because we're spending more input tokens, more output tokens, and depending on the models involved at different steps, they may be more costly than others. Yes, question.
For the models that you use, are they fine-tuned, or like you mentioned reasoning over fine-tuned, but did you provide any particular remediation, I guess it might be a lack of knowledge on my part whether or not that's different from fine tuning. And like, which models have you found useful for which parts of the chain of prompts?
Yeah, good question. So we are not using fine tuning, and just to be clear on terminology, fine tuning would imply that you have a set of training data that you are going to apply to an existing model to refine it in a particular way. So you're making it more directed towards a particular task. We have not explored that, and we honestly, it might be unfair, but we have a bias towards thinking that's not going to be super effective because the sort of foundational flagship models already know a pretty good amount about security. What we do, which is what you're asking, is we do provide many examples within our prompts. So this is referred to as like few-shot prompting, where maybe I have 3 examples of what a fix for SQL injection would look like. And then, yes, also trying to provide as much context as possible. Like here's what the vulnerability class is, here's what typical remediation examples look like, here's how you want to fix it in this case or that case. We find that to be very effective, and so we don't feel the need to do fine tuning. Did that answer your whole question?
If you can share which models
Oh, yeah, sorry.
are effective for which pieces.
So I talked about 2 different kinds of a couple slides back, if I can get back. When we're sort of building the instructions, which may be fed to another model, we found that the reasoning models are very effective at that. When it comes to actually making code changes themselves, I think that the reasoning models are overkill, and they don't necessarily produce the best results either. So that the code change itself may be made by a model like GPT-4o. For a while, it was GPT-4 Turbo. But yeah, when you needed to come up with a plan and gather as much context as it can, the reasoning models seem to be the best choice for that. Yes, question there.
So in your opinion, how much hallucination do you think is not applicable while remediating any task?
Sorry, can you repeat?
In your opinion, how much hallucination is acceptable?
Oh, okay. Yeah, how much hallucination? It's sort of a cop-out answer. It sort of depends. It depends on how you're prompting, and it depends on how you're building these chains of reasoning and chains of processing. I think that if you were just to go to ChatGPT with a reasonably complicated piece of code and say, hey, I think there's a SQL injection vulnerability on line, whatever, 100, please fix it for me, I would say there's a 50-50 chance that the model is maybe not going to get the fix wrong, but it's going to add something that you didn't want it to add. You need to be really very specific with constraining what you're asking for. So saying things like, don't add or remove comments, don't add or remove white space, don't try to fix the problem that's really another problem that's over here, and I'm only asking you to look at this thing. It will be very proactive. It's trying, I don't want to humanize it, but it seems like it's trying to be very helpful, and I appreciate that. But when you're trying to build something very automated and very targeted, that's not helpful at all. When you really constrain the solution space with good prompting, you do see hallucinations still, I think at a much lower rate, but the way we account for that is by building in feedback loops and asking it to evaluate itself on how well it completed that task. Sorry, is that my all done? Yep, all done, sorry. I'd like to take one more question, but I'm getting the sign that we're all done here, so I'd be happy to talk to you afterwards. So thank you very much again for all your time, and enjoy the rest of the conference.